Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Hello, this is Kirk Gray.
And this is Fred Schenkelberg. Welcome to Speaking of Reliability. Hey, we got a question the other day, and I hesitated bringing it up to you, but then we started chatting about it, and I said, oh, wait a sec, let's hit record. So the question was around accelerated life testing. And one of the ways to do accelerated life testing is usually you have to know what the failure mechanism is. It might be cracking, it might be this, or it might be that, whatever, but it's usually focused on a particular failure mechanism. And it wasn't clear whether they were, what the subject of the testing was or what mechanism they were actually involved in. But they said they set up and described a way of doing accelerated testing, which is pretty common. You use 3 different stress levels for a particular stress, like a low, medium, and high temperature.
Right. That
all of them should create failures in a reasonable amount of time. And then you get a relationship between the amount of stress, how high the temperature is, for example, versus the time to failure. And then you can create a relationship to hopefully project back to use conditions.
Right. Stress level versus when it wears out. And that's what you're looking for, not for finding defects, which may actually occur during the accelerated testing.
So, which is a problem because then it
is a
screws
problem
up your sample size.
Right. Unless you do a very detailed, sometimes a decapsulation or something like that to find that, the silicon chip actually had a poor line width and something. There's those kind of things.
Well, there's all kinds of things that can happen.
All things that kind of happen. But you just say this is a nominal device that's been around for a while, and
but I don't know what they were testing, if it was a component or a material or a whole system. It wasn't and so I'm waiting for a response from that.
Right.
But typically, the way that test was described, it would be, I have a specific failure mechanism, and I know that this stress accelerates it to some, it is involved in making it go faster.
Right.
And so everything was looking good.
Right.
And in the way they're describing, okay, you're on track. Yeah, well, that's fine. What are you testing, kind of thing? Because that's a separate question. We'll come back to that.
Right.
And then it was, we're also going to apply 3 different, so low, medium, high power and a low, medium, high humidity. Or I don't remember exactly what the stresses were, but they were going to do 3 different stresses, but only have 3, set. The rest of it looked like it was for a single stress. And I'm like, even with 2, it gets really complicated trying to figure out, what stress is accelerating what. And one of the things that's really difficult is, if I add more power to a powered up electronic system, for example, it will increase the heat a lot of times. And so that is now intermingling with just the temperature one, for example.
Right.
And so what's due to power and what's due to heat, or what's due to just temperature, or do they interact and create all kinds of other weird stuff?
And we know that certain stresses, like, for instance, vibration and or thermal cycling, both accelerate a cracked solder joint.
Right.
Okay.
In slightly different ways, but they both
in slightly different ways. Yeah. And that crack will propagate differently or different when at different temperatures.
Yep.
At a cold temperature, it's probably going to be much more brittle, and that vibration, and it's also going to change the frequency of the resonant frequency of the FR4 material, whatever the substrate is,
whatever
that
it's
attached to. Yeah.
And it might dampen, you get to a higher temperature, it's going to dampen the impact of the vibration. It's going to make it softer. Yeah.
Right.
So it was one of those that it just brought up, that just throws a wrench in the whole thing, and I was like, how are you going to relate the 3 different stress so there's 9 different things. And if they're all absolutely independent,
Yeah.
you would need 9 or 12 sets of conditions to run this.
Right.
I'm like, no, let's step, and then I had the thought, and it's why I asked, it's like, well, are you testing the whole, like a whole box or a whole subsystem? Say a power supply. I have no idea what it is, but let's say it's a power supply. So there's solder joints, there's components, there's capacitors, there's, diodes, there's op amps, there's, CMOS stuff, there's analog stuff, and all the other things that are on a power supply.
Right. There's especially transformers, heavy components. There's not, it's kind of comprehensive.
Yeah. And so now on that single power supply, there's probably 3 or 4 different 100 ways it could fail. Some are more common than others.
Right.
But then you add 3 different stresses, and I bet you it's going to accelerate 3 different things.
Right.
That's why we do HALT, right? We use multiple stresses to expose the different failure mechanisms.
But in HALT, and this is what my recommendation always is, until you really have a lot of experience with your product and putting it under the stresses, is that you use a single stress at a time.
Oh, yeah.
And you don't put vibration and thermal cycling together right away. You first find the boundaries of each individual stress. Okay. Then you start combining them. And you can start, you can power cycling, vibration, thermal cycling all at the same time after you've found what the power
the individual ones
are. Or voltage, or if you're doing voltage margin, what each individual voltage limit is for function, operation, maybe destruct sometimes. It's not always
depends
necessary.
Depends on how many samples you have.
Right. Depends on how many samples. And a lot of times you can't destroy it before it quits operating. Right. It quit operating before you reach a destruct level.
Yeah.
But, that makes it just, if you add, as you just mentioned, if you put a combination of stresses together, you really can have a hard time determining, first of all, which stress really accelerated the mechanism, which was a dominant accelerant versus a modified, maybe temperature and vibration. What was it, the vibration or thermal cycling? Both can crack. That's why once you find this, this like cracked solder joint under whatever conditions you have, the first thing to do is evaluate, well, was that a nominal solder joint that would be produced on the line all the time, or,
or is that a repaired solder joint, which is,
or is that a repaired solder joint? Somebody hand soldered it.
Yeah.
Or is this something that can be, and is this something that we can easily improve by the pad size, the pad width, something like that?
The amount of solder,
or
the types
the design before, you bought 10 million boards. So anyway, that's the whole idea, is keep it simple as we talk about KISS. and keep it simple at first, but then you add more complex things on top of it. And so for this company that wants to accelerate using 2 accelerating factors.
Three, yeah.
They can't, 3 levels of accelerating factors without knowing, knowing the boundaries, the limits of the device under each individual stress gives you the opportunity to increase the stress levels. What they're trying to do is quantify. I think what they're trying to do is form an equation to quantify. And that's even more difficult. And I also feel for most electronics, for the vast majority, 90% of the electronics, knowing how long it's going to last is mostly irrelevant because of technological obsolescence.
Yeah, no, we've talked about that before. No,
anyway, we'll talk about that. But
Kirk is, I don't know. What I don't know is it even electronics? We jumped into that just an assumption. So I don't know.
Right.
But just the point is that we use, like in HALT, we use multiple stresses to deliberately to reveal things that individual stresses often don't show or don't show very quickly.
Well,
and there's all kinds of interactions between stresses.
Correct.
That's an advantage. So it's that concept that says when you start adding different stressors to an accelerated test and you're trying to figure out how long is it going to last. And that was the model they were using. They're trying to create an equation for acceleration factor. Is that each stress typically has one, not all stresses accelerate the same failure mechanism. And you have to really know your product or material or system or whatever it is that's the single thing that's going to happen.
Right.
But the likelihood that 3 different stress levels, and I'm just using power as an example, versus 3 different stress levels and temperature, probably create a different acceleration factor. They don't have an equal relationship. 1 degree increase equals 1, week shorter lifetime versus 1 volt or amp higher in power equals 1 week. Now, if you make that assumption, that's the way the test was designed, is like, if you make the assumption they all will create the exact same acceleration factor, you don't know what you're getting. How in the world are you going to model
you're modifying it when you're adding the other one, right?
Yeah.
This is why,
This is why you don't like statistics.
Well, no, if it was a mechanical gearing system, and they were trying different lubricants at different temperatures, maybe, they could measure something where they could measure wear or life degradation, where they could actually take the gears or the assembly and see how much material has been. They could either weigh it or, actually measure it physically with
or even oil analysis. They can take a look at how much particulates in it.
Right, exactly. So that and we know that,
But let's say you're doing
rubber tire it's going to wear.
No, Kirk. Let's say you're doing a gearbox, right? Okay. And you just run it faster, or you cycle it, or 2 different ways to stress those. Another one is you put a unbalanced load on it. Right. And so let's say you run all 3 of those. Right. And all of them could cause failure. Right. But the unbalanced load is more likely to destroy the bearings. Right. Right. The temperature or, running it faster will degrade the grease quicker, but not necessarily then it'll just keep running, if you don't stop it, kind of thing. And eventually the bearings will go and so on.
The viscosity of the grease or whatever changes if it's high temperature. Yeah. And in fact,
it'll fall out or leak out.
Putting an unbalanced load on is also going to cause more friction and probably heat the gears up.
Add more heat, yeah. So accelerated testing in and of itself doesn't matter what technique or style of accelerants you're using, or if you're using an existing model or trying to create one. You really, really, really have to understand what the failure mechanism is and understand that the stresses interact with that failure mechanism. As soon as you go beyond that, and I've seen people try to take, I got 6 prototypes here, full systems, full prototypes, and we're going to throw them in hot chambers, and check them every now and then, see if they're still working. And I says, well, so why are you doing that?
I know.
And they were going to use that to estimate its, how long it'll last. And I'm like, you've got thousands of failure mechanisms in there. What if the 3 that fail have completely different mechanisms? Right. And then 2 of them fall out because you had poor soldering or you had, assembly defects, which is
right. Which is what the majority of failures are probably going to come from in the 2 to 5 years time frame that this maybe system is being produced. Yeah. Anyway, yes, this. So when you get that kind of question, Fred, when you hear this, we're going to use 3 different levels with a bunch of combined with 2 or more stresses at each level. Do you ask what they're trying to accomplish?
Oh, yeah. No, I asked, and it was clear.
It was to find out how long it'll last in the field?
Yeah, no, it was right up front. Their objective was to create an acceleration factor so that they can estimate how long it'll last in the field. And they wanted it to go faster, testing to go faster.
Everybody would do that, right?
But it's one of the things I find with accelerated testing is if you can run it at nominal loads with, how a customer would use it. Right. Is the best way to estimate how long it's going to last in the field. And even then, the lab is often not the same as in the field. So you got to, I'm thinking of inkjet printers. It's the fans pulling in all kinds of dust and debris and pet dander and everything else. And
Exactly. You're talking about controlled environment in a chamber at very controlled levels versus whatever the end use environment is. And certainly there's some that are more uniform than others, but say for any consumer product or any outdoor environmental product that's used outdoors, those conditions are going to vary widely if it's sold anywhere across, if it's sold nationwide, that's the use conditions, and even internally in a house.
Or even how people use it in different, And
if they're next to a coal plant, tell them anything.
If they're next to an ore plant and they got a bunch of rock dust all over the place, or on the coast and they got a lot of salt fog.
Right. So it's kind of a delusion that I see these companies making to think that, okay, they're doing reliability and they're figuring it out. When I have always taken the orientation that inherently most circuit boards and systems are pretty robust, and there's special cases where new technologies come along that you want to find out, the weaknesses. And I think using combined stress environments, and if you want to do 3 levels, that's fine. It's fine, but don't think that you're really being able to quantify it, and you're not also taking into consideration that the variation in manufacturing is going to be an issue, and it probably was going to be leading to, and as not only in your manufacturing, but in all your suppliers' manufacturing, and in the chain, and most of the failures are going to be assignable causes. I'm absolutely certain of that. They're not going to be common cause wear out unless somebody did a poor design. But there are some mechanical systems, tires, gears, even LEDs may have decay over time. But some of these lifetimes of the in lifetime entitlement of especially semiconductor devices, but even circuit boards and systems, is quite long, and you're really going to be shorting almost all of those. Is my experience in 30 years I've been looking at failures, that almost all of those are going to be, the vast majority are going to be assignable. Some you can't really find out what the root cause is because they're destroyed. You send them back as, we talk about to the supplier, and they don't want to deal with a little chip or 5 chips that have failed. And if you're not a big customer like a Dell or an HP or something, they're not.
That's a whole nother podcast there, how to deal with suppliers when you're a small buyer. But it's quantifying. It's quantifying field life, which has been a main challenge for all reliability engineering. And like I said, I sat in a committee that talked about, or wanted the VP of manufacturing wanted to know why the reliability predictions were not matching the actual field failures. That's a good question.
It's a good question. And nobody could really ask.
Well, there is a real answer, is that we're using really bogus old data on a nonsensical combination, and we create a number. It has nothing to do with how the product's used in the field or what its risks are.
No, but this is a big company. Storage technology doesn't exist anymore. And they had a whole reliability prediction department, which I, as a reliability testing guy, never heard from. They never asked me what fails in the test. They never even, I don't even know if they knew what failed in the field. They were using the old data, like 217 or,
some
whatever
variant of it.
Some FIDEs, I don't know. But it's nothing to do with what that company's failures were, or our company's failure, So of course it didn't correlate. Never did.
Never would.
Never did. And so why did they have this department? I don't know. It's, because it's reliability engineering built on some general belief that you can predict, and at one time you might have been able to accurately the lifetime of electronic hardware.
Well, it's
not possible.
It is possible. One, there's 2 ways. There's 2 ways it can work.
Weather.
No, Kirk. There's
from now.
There's there are 2 ways it can work. A parts count prediction could be randomly lucky and actually to be very accurate. It's very rare. And when I was at Hewlett Packard, when the early days of them getting into the, like in the 60s, 70s, and it was all test and measurement equipment primarily. Yeah. They did detailed failure analysis. They were very vertically integrated. I mean, they even made their own screws at one time. Yeah. And so they did everything that came back and everything they could get back. I mean, these were expensive units, so they did the repairs on them. They did detailed failure analysis and kept track of all that. So they had their products with their components in their manufacturing, and they had the great failure analysis stuff.
And they had all control of it. Right. They had
and so they were able to be pretty close. But as they started doing more consumer products, they started doing more, we're going to replace the whole board versus just the component. We're not doing failure analysis. That deteriorated pretty quickly. And they stopped using it because they then found that it wasn't useful. And so the concept works, but it really depends on really good failure analysis and detailed analysis.
Right. And that was the important part of the feedback is, it's like the stone soup, get the rock and put it in, after you put all the veg. Yeah, it was the detailed failure analysis and understanding the physical mechanisms that caused the failure that helped them improve the product. Yeah. Not that they did a parts count or anything like that. And as they say, those predictions, a broken clock is correct twice a day.
Right.
So
that's what I mean.
Yeah. They hit a number and somebody said, okay, but that was only that week of that year or something.
That's right.
It's all up and down.
Yeah. So anyway, back to the question we got is we sent back a couple of comments and questions on it, and I haven't got a response yet. And so it was, we'll see how it turns out. But if you're getting into a realm that, there are some things that we do in reliability engineering that you really need to understand what you're doing and what the assumptions are, and is it useful for you? Or, you got to back up. What are you trying to achieve? And here, at least, it seemed pretty clear. They wanted to run a test quickly to come up with the expected lifetime of this product, and for whatever reason, whatever system or product or element they were working with. But that's a common task. It's fraught with.
It's fraught with
all kinds of bad techniques. Yeah, all kinds of bad things. But it can be done if you're, lots of different conditions around it. But the unfortunate part is that I see way too many that are just, what? Why is that? But anyway, we can talk about that another time.
Okay, yeah, they will get benefit out of this. Okay, if even in the testing they do get failures and they do failure analysis and understand what the mechanism is, whether they want to quantify the whole thing, fine. I mean, I think that's
fraught with. That's
misleading
really
because
lucky.
They're in a controlled environment and the field is not, and also they're using a very small sample size, and their production, depending on what its volume is, going to have quite a bit over the years or months that they're going to produce the product. So, it's just. But if they get do the testing and find a failure, they may not know what the main driving force is, but they know that they need to improve that strength of that element in the design, maybe.
Or design out the failure mechanisms. There's all kinds of good stuff that could come from it. But in my estimate is, from our discussion, I'd say, why don't you take those samples and go do halt testing? Do that instead. You'd probably get a lot more value out of it. Right. But anyway, so the point is that, we get questions. Some we kind of go, what are you trying to do? And others like, that's a good question. Well, either way, it's a good question, but
either way,
that's an interesting approach. Yeah. Let me think about that.
Yeah. And I think we understand where they're coming from, whether it's correct or wrong.
Yeah. Well, I don't know about correct or wrong, but it's more, will this yield the results you're expecting in a meaningful way? Will this give you an answer that's useful or information that's useful? And, so if you're listening to this and you're setting up to run a test of some sort, or you're running some activity and you're not sure, if you got all the assumptions covered and know it's going to be useful or not, let us know. Kirk and I will tear it apart and tell you, what to do different. but please do send us over your comments and questions. One is we can help you, get on track or confirm that you are on the right track and all that good stuff. That's all good. You got somebody to take another pair of eyes and take a look at it. But also it gives us fodder for a discussion here on the podcast. I think we're getting close to 875 episodes. I think the next one's going to be that. But yeah, we're chugging along, having a good time talking about a handful of these questions that we get on time to time. And we look forward to hearing from you. Head over to sendoreliability.com/go/SOR. You can find a couple of ways to get in touch with us. Kirk and I and the other hosts of the show are available through LinkedIn or our about pages on the site. So, Kirk, you going to go break something later today?
Well, I never intend to, but yes.
Well said.
But something may break on the way. Anyway,
right.
Yeah, it's always an adventure. Life is an adventure, and hopefully everybody's having a safe one.
That's right. All right. Well, thanks much, Kirk. We'll talk to you again soon.
All right. Talk to you later, Fred.
Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.